All right, we're going to be talking through the winter paper of 2014, and this is paper number 11. Let's jump straight in. Okay, so basically what they wanted you to calculate here was the volume of each of the steel balls. You simply measured the difference in the volume, the difference in the volume with the balls in and out, and divided by 5, and you should get 6 centimeters. This graph shows speed of car changes with the time. When is the car stationary? Well, when the car is not moving, when the speed is 0, the speed is 0 over here. Answer is D. Okay, a man stands by a railroad track. Trains moving at 40 meters per second. It takes 2 seconds to move past them. The answer is D, simply times the speed by the time it takes, and you'll get the distance. Okay. The mass of an astronaut is 70 kilograms on the moon. What is his mass on Earth? Well, the mass doesn't change regardless of where you are. So it's 70 kilograms. All right, so this was just, basically trying to illustrate how a mass balance works. If you looked at these two things, it sort of sticks either one side or the other side. And if you go, this is about, if you add this all up, it is 1, that's 2, that's about 0.7. If you add this up, that is 2.7, and then that should be 1, 2, and that should be 3.1. So the weight must, because it slides to one side the one way and slides to the other side the other way, that means it must sit in between these two values. So it's not that value, it needs to sit in between, and bam. All right, this is just asking you to calculate the density. So you just need to divide the mass by the volume. Oh, what is the volume? It's that times by that times by that. But the mass, just divide through mass divided by the volume, we'll get the density of the metal. All right, in which situation is no resultant force needed? Well, if it's changing direction, it will have some form of acceleration, whether it be centripetal acceleration if it is moving in a circle. If the car is slowing down, it's obviously decelerating. If it's speeding up, and it's accelerating, any form of acceleration needs a force. But if it's moving in a straight line and at a steady speed, it requires no force. So the answer is B. Which property of the bodies can be changed by applying a force to the body? So we can change the motion, the shape, but not the mass. So that's the correct answer. The mass, the shape, but not the motion. Well, you can't change the mass with a force. You can't change the mass with a force, and you can't change the mass with a force. So all of those are wrong. And bottom one is then therefore correct. All right. The list contains 3 energy sources. Blah blah blah. Which of these sources are renewable? Well, the answer here is geothermal and sunlight on a solar panel, and nuclear fission is not. Technically, geothermal is not renewable because it does have a limited source. I mean, technically, even sunlight is then. They're both sort of, this is just the time scale of which these things would run out would be massively different. It would probably go in the order of, fuels for this would run out first, then geothermal would run out, and then sunlight would probably run out eventually. But yeah, for a practical answer, it is B. Okay, this is just which statement about the pressure of the water on the base of each container is correct. These containers all have water level at the same height. They just have different shapes. The water pressure is the same for all 3 containers. Well, yes, the height is the same, so therefore the hydrostatic pressure, or pressure induced from the mass of water, it will be the same. The others are wrong. The water pressure, none of these are correct. Okay, which movement will require the greatest amount of work to be done? Okay, so it's it's force times by distance for work done. Okay, so we just look at the one with the highest force and the highest distance, and that is the bottom one. All right, it's connected to a gas supply. There is a gas leak, and the pressure on this side falls. Okay, what happens to the water level P, and what happens to the water level at Q? So if the pressure here falls, this is going to be then like trying to regain equilibrium at a lower pressure. So the water is going to try and sort of move in this direction. And as it moves in this direction, P rises, Q sinks, and there we have it, number C. All right. The diagram shows, okay, it's just basically asking you which molecule in this container is most likely to escape. So two things for it to escape. It needs to be close to the surface, so we can already rule out those two. But then it also, the one that's more likely to escape is going to be the one with the higher energy level. It gets away from the bonds, so it's going to be the higher energy one. All right. Some gas is trapped in a container of fixed volume. The temperature of the gas increases. All right. What happens when we increase temperature at a fixed volume? The pressure goes up. The answer is D. All right. Okay, the answer to this one is just quite simply C. We can move on. The equal masses of two different liquids are put into identical beakers. Liquid 1 is heated for 100 seconds and liquid 2 is heated for 200 seconds by the heaters of the same power. So about double the energy is going in. The temperature of both liquids increases by the same amount. Thermal capacity. So the answer is D. The thermal capacity of liquid 1 is less than the thermal capacity of liquid 2 because the temperatures have changed by the same amount, but this guy had 2 times the energy put in, so therefore it must have a higher capacity such that the temperature didn't rise as much. All right. The metal surface of a kettle is hot. All right. What happens to the cool air outside the kettle when it comes into contact with the hot kettle? Okay. The density of the air decreases and the air rises. So that is the correct answer. These are definitely wrong because the density of the air does not. The density does not decrease because it's being heated. The volume increases. The density of the air increases, but it doesn't fall because the buoyancy is actually going up because it displaces more air. So the answer is B. All right. One type of double glazing consists of two planes of glass separated by a vacuum. Okay. The idea is to try and stop the transfer of, let's say, this is inside, this is out. Actually, let's draw this a little bit neater. Second. So this is inside, this is outside. And we basically we want to try and stop the energy from the thermal energy from getting across. So there is no air inside here. Okay, so that's going to stop both conduction and convection. There could technically be a small amount of conduction across these little gaps here, where actually, you're holding it in. That's basically would be the boundary of the window. But since there's nothing to transport the heat across, the only thing that can get across is radiation. And so the ones that are prevented are conduction and convection. All right, this is basically just reading the graphs correctly since they have the same scaling. What statement is correct? The statement that is correct is the amplitude of the wave P is the same as the amplitude of the wave R. And you can see it, they both have the same amplitude. Excuse me. All right, let's keep moving. Okay, light waves pass from air into gas and are refracted. What always remains constant when this happens? It's the frequency. All right, so the speed is changing. So the speed of is changing. but the frequency is not. But the wavelength is also changing. So the speed is going down. Okay, if this is remaining constant, the wavelength also goes down. So that's also why that one is not a constant. So the answer is the frequency. All right. What type of electromagnetic wave is used in airport security scanners? Well, it's going to be X-rays. Okay, if it was microwaves, that would be cooking us, and not that wouldn't be too great. Infrared would be, well, also that would be heating us up in a different way. Radio waves would be too long in wavelength to penetrate through or interact with us in any meaningful way. Because actually, also not just from the penetration point of view, but also because they would not they would not be able to interact because of their large wavelength compared to the size of us. So the answer is X-rays. I suppose they mean airport security scanners for maybe your baggage, not you as a person. They don't have those. Anyway, but it would heat up water if it was microwaves and infrared. Which waves are longitudinal? The answer is D. Sound waves are longitudinal. These two are, this is electromagnetic, these two electromagnetic radiation. These are surface waves, but as we know, they make sort of that pattern. But these are the longitudinal ones that expand and contract as they move forward. Well, in this case, like that. All right. An object is placed in front of a converging lens. The lens has a focal point F, which is over here. So they basically want you to tell you what labeled position in the is the object placed, and the keywords are placed in. The lens produces a real enlarged image. All right. The fact that it's enlarged means, well, I can't set it C because that would be the focal point, because there would be no image. It would all be compressed into a, well, in reality, not all the way to an infinitely small thing, but very small. And then as we move out this way, we actually get the focal. Being out here would be too far, because this would be then outside. The image would then be reduced quality. Oh, not reduced quality, but this wouldn't be focusing it onto anything effectively. It would be then creating a larger projection. Okay. A fire alarm is not loud enough, and the pitch is too. Fire alarm is not loud enough. The pitch is too low. An engineer adjusts the alarm so that it produces a louder note of a higher pitch. All right, so produces a louder note of a higher pitch. Okay, so the keywords are louder note, or just louder, and higher, and then pitch. Okay, louder just means increased amplitude, so larger amplitude. Higher pitch, is the same as frequency, so a higher frequency. So the answer is A. All right, in an experiment to measure the speed of sound, a student uses a stopwatch to find the time taken for a sound wave to travel from X to Y. She does this 6 times. Table shows the results. Which value for the time should be used to calculate the speed? I'm wondering if it's just taking first measurement. Suppose you would take the average, which I think in the answers would be C. I would take the average. I mean, I suppose the most reoccurring, or the closest to the most recurring, is you got 5 here, you got 5 there, you got a 6, you got 1, 7, which sort of balances out with that. So yeah, I'd say the average is probably around 0.6. It's most likely the arithmetic mean. Okay, the ends of 3 metal rods are tested by holding Q to rod 1, the side Q of rod 1 to the others. And this is what happens. This attracts R. It also attracts S. And it attracts T, but it repels U. Okay, so we know that therefore, like, these two are different, and this is only the case if this one's a magnet. The fact that this attracts both sides suggests that this is not a magnet, and for this one to have repelled any of these and or retracted any of the others, this must be a magnet. So this guy's a magnet, this guy's a magnet, and so the answer is C. All right, a permanent magnet is made from metal, and an electromagnet uses a metal core. Which metal is suitable for each of these purposes? This has got to do with just soft and hard magnets. For a permanent magnet, we want a hard magnet, and for an electromagnet, we want a soft magnet because we want it to change quickly. So we know that iron is a soft magnetic material, and steel is a hard magnetic material. This is most likely due to like the grain boundary structures being different in steel and iron, but you guys don't need to worry about that. So the answer is C. Steel for permanent, iron for electro. Okay, which row gives you the units for energy and the unit for electromotive force? Okay, it's a pretty straightforward one. We know that energy is a J. It's not watts. Okay, this is joules. Watts would be power. So energy per unit time. And for EMF, we know that it is a V. Newtons is a force. All right. Okay, a student carries out an experiment to investigate the resistance of a resistor. She takes a series. Well, let's just jump straight forward. She's basically trying to measure the resistance of this guy over here. Okay. And the answer is A, because she needs to measure the voltage drop as well as the current going through this specific resistor. It'd be useless in case of these other things where you're measuring other bits. So that would work in terms of the current, but wouldn't in terms of the voltage. And it's similar with the other ones. This is across the variable resistor, which makes no sense. That makes no sense, and that makes no sense. And so that is the one that we would need. All right, the diagram shows this sort of setup. Okay. They're asking what would the ammeter read if we close the circuit. Okay, we need to combine two things here. We need to calculate the resistance now in series. So it's just 1 over R is equal to 1 over R1, 1 over R2, and you have to do some stuff with the fractions, but you'll get to basically, you'll work out the resistance being 6 over, I think it's going to be, hold on a second, let's just quickly do it. It's going to be, so 1 over R is going to equal to, and now I'm just going to go straight into finding a common denominator. So it's going to be it's going to be 2 over 6, and it's going to be 3 over 6. We add those up. Okay, so we can get 5 over 6. So we're going to get the resistance is being 6 over 5, right? And we know that V equals IR, so we're going to say, so we rearrange that to get R on its own. So I is equal to V divided by R, right? And that's we're gonna have to move over here. We're gonna have to get, so then what we're gonna get is we're gonna get D, because we're gonna get the 6's canceling. So we're gonna get 5 over 6 multiplied by 6, current I, which is equal to 5, which is D. All right, so just to sum it up, calculate the resistance in parallel, apply that equation, and you should get the answer. Okay, this is a really simple one. The diagram shows a torch containing 2 cells. You can kind of already see if you draw like the loop inside there, there's the switch, there's the light. So the answer is A. Got 2 batteries, in series. Then you get the switch, then you get the light, and then back to the batteries again. So we can see that in there. All right. Okay, this is just a quick question on a voltage divider. We just need to use the voltage divider formula, which I've written down over here. So basically, we need a 1, because we got the amount here, we need a 1 on the, we need a 1 on the top and a 10 on the bottom. What numbers can we combine? So we can have the 1. If we need a 1 on the top, we're going to need y to be 1, resistor y to be 1, and then to get a 10 on the bottom, this has to be 9. So the answer is C. All right. The current in the kettle is 10 amps. So you're basically applying too much current through the resistor. The fuse blows and the kettle is undamaged. Well, the reason why, the whole point of the resistor is to stop the kettle from being damaged and also stop fires from happening. That's why it's very important to match your resistors correctly. Okay, this is just a quick question on why they use high voltage power lines as opposed to low voltage with higher current. So power is equal to the voltage times by the current. Basically, if you up the voltage, you have a lower current, and your heat loss is proportional to your current. So you want lines that have basically low current, high voltage, and that's why the answer is B. All right. Okay, this is just showing which diagram. So we know that it goes around the wire, so it could be either of these initially. But if we look at how the lines are forming, you get the lines more tightly packed. In other words, magnetic field is stronger, closer to the wire, so therefore B is the answer. All right, the diagram shows a simple transformer. All right, and we're just basically trying to figure out like the windings. So if we know that it's going from 240 down to 40, that's 1/6. So the windings must be doing the same thing. All right, cool. All right, in a cathode ray tube, hot tungsten cathode releases this. Okay, so this gives you a little bit of a hint. Cathode, usually negative. Thermionic is just like the emission type. What are these particles? Well, they're electrons. It's not like the tungsten atoms get ejected. The protons wouldn't, because they're locked up nice and tight in the nucleus and alpha particles. This is not a form of, it's not that form. It's not your classic radiation. It's thermionic emission. All right. The diagram shows a radioactive source and a thick, that's the key word is, nice, thick aluminium plate, aluminium sheet, and a radiator detector. The radiation detector shows the reading greater than the background readings. In other words, it's picking up additional radiation. Which type of radiation is being emitted by the source? By the source and detected by the detector. It is going to be gamma. Okay, so alpha is too big, wouldn't get through. Neither would beta. So this would be interesting. So if the source was emitting enough infrared to start heating this plate up, you could get re-emission on the other side for infrared. But that, because this most likely is a small amount, it probably diffuses the heat if it were to be infrared. Um, so it's most likely going to be gamma, because gamma's got enough energy to get through this. You would need to chuck in a piece of lead maybe to stop it. All right. This is just another half-life question. And it says, estimate, what estimate of the half-life can we be obtained from these readings? So we basically want to take this number and find like where it's roughly half. and it sits in between these two. So therefore, 2 to 3 hours, and that's why the answer is B. All right, a nucleotide represented by the symbol blah blah. How many neutrons are in one nucleus of the nucleotide? Okay, so the top number is the mass number, right? Which is the neutrons plus the protons. They roughly have similar masses. And then the bottom one is just the proton, the atomic number, which is, let's just call that A, the atomic number, which is just the protons. Okay, so how many neutrons? Okay, so if the top number is the neutrons plus the protons, we need to minus off the protons. So we take the top number and we minus off the bottom number. So that is that one over there. All right, guys. Thanks for listening to that. See you guys soon.